Today we're going to discuss the DC analysis of the common collector, or otherwise known as the emitter follower configuration. This is the third configuration of the BJT. This is the circuit. The collector is directly connected to the ground. The input coupling capacitor ay naka-apply sa ating base because the base is the input terminal of the common collector configuration. The output coupling capacitor is connected to the emitter because the emitter is the output terminal of the common collector configuration. What if nagpasok tayo ng isang signal dito sa ating input coupling capacitor? For example, a sine wave. What will be the corresponding output? Ang output natin will almost be the same. No, almost equal yung input signal natin dun sa output signal. Anong silbi nung ipinasok mo, yun din ang lalabas. No? Bakit hindi na lang natin idirekta yung source na to pagdating sa ating load sa output? It's because the common collector configuration is used as an impedance matching circuit. Unlike the common base and the common emitter na ginagamit natin for voltage amplification, ang common collector ay hindi natin ginagamit bilang isang amplifier. So para mas maintindihan natin yon, let us recap yung tinatawag na loading effect na pinag-aralan natin sa electronics and basic circuits. For example, meron tayong high impedance na source. So this is high impedance. Right? So nagpo-produce siya, for example, a sine wave. Meron siyang sine wave na output, no? And we have a low impedance na load. Right. If we directly connect the low impedance load sa high impedance na circuit, which will provide you with a signal, no? What will happen is, liliit na yung signal natin dito. No? Dahil nagkakaroon na tayo ng loading effect. Right? If we will disconnect it, for example, our output may be ganito kalaki. If we connect the low impedance load, ang output natin, maaring ganito na lang. So that is the loading effect. Yung pagbaba ng value or amplitude or amount ng voltage because we have connected a low impedance load sa isang high impedance na circuit. So in order for us to rectify or correct the mismatch between the two, yung high impedance at yung low impedance na yon, nagkakabit tayo ng circuit sa pagitan nila. So let us draw a block diagram or a block symbol to represent the impedance matching circuit. So maglalagay tayo sa pagitan nila. So this is your impedance matching circuit. And then this is your low impedance na load. In that case, kung ano yung ipinasok mo dito, more likely, yun din yung lalabas dito. Unlike kanina, nung dinirektang i-connect natin yung low impedance na load dito sa ating high impedance na circuit, bumaba yung voltahe natin or yung amplitude. So that is the role of the common collector configuration. It's used as an impedance matching circuit. In our example, pinapahanap sa atin dito yung VCEQ, which is the collector to emitter voltage at the Q point, and the emitter current or I sub E, because we all know V sub CE is the output voltage and I sub E is the output current for the common collector. Actually, yung mga common emitter na pinag-aralan natin before can also be used as a common collector. But to be more specific, ganitong circuit ang gagamitin natin. Ang unang gagawin natin dito ay kukunin natin yung kuryente na I sub B based on or from the base and emitter junctions. Let us now draw the equivalent circuit ng base and emitter junctions or terminals. Let us label that B and E. Lahat ng capacitors are considered to be open circuits pagdating sa DC analysis. Let us draw the equivalent circuit. Iahang muna natin si collector pansamantala kasi hindi naman siya kasali dito sa base and emitter junction or terminals. No? So this is your 240 kilo ohm resistor, which is your R sub B. And then you have R sub E. which is equal to 2 kilo ohms. And then, yung R sub E natin nakakonekta dito sa VEE, na yung negative polarity ay nakakonekta dun sa RE. That's why we will have this orientation for VEE, which is equal to 20 volts. Hindi na natin kailangang ilagay yung negative na sign dun sa 20 volts kasi it's understood with this schematic symbol na negative yung nakakonect sa ating R sub E. Ang susunod na step dito ay yung parang ginagawa lang natin sa DC analysis, no? We'll just write down the induced polarities and the induced voltages and the induced currents. No? So we will follow the orientation of this source. This is minus. This is plus. This is minus. This is plus kasi meron tayong VBE doon. And then this is plus. And this is minus. Alright. These are the induced polarities for the induced voltages. Next are the induced currents. So, anong kuryenteng dumaraan kay R sub B? Since konektado siya sa ating base, ang dumadaan sa kanyang kuryente is I sub B. But what is the direction? So, papasok yung ating I sub B dito sa ating base because we're using an NPN transistor. What about for R sub E? Ang dumadaan sa kanyang kuryente ay I sub E. So we'll just follow the arrow. Ang direction is palabas or pababa dito sa ating R sub E. This is your I sub E. So this is the equivalent circuit for the base emitter terminals or junction. Now we're going to write the KVL equation for the base and emitter junction or terminal. Gagamit ulit tayo ng clockwise direction for our KVL equation. Papasok tayo sa plus nun. So we have positive IB times RB. So I'll just write down first yung mga unknowns or rather yung mga variables natin. No? And then papasok tayo dito plus. Ang voltahe natin dito ay VBE plus VBE or the base and emitter junction, base to emitter voltage rather. And then we have plus IE times RE. And then minus 20 volts, or which is VEE, equals 0. Ang gusto natin makuha dito is yung I sub B. But we should express I sub E in terms of I sub B. We all know that I sub E is equal to beta plus 1 times IB. So we can replace I sub E dito no? In terms of I sub B. Right, so we have IB, RB, plus VBE, plus, instead of using IE, gagamitin natin yung beta plus 1 times IB times RE. So, pinalitan lang natin yon. Minus VEE equals 0 volt. Alright? Next, i-isolate natin ngayon si I sub B or IB. We have IB times RB. So, ito yon. And then this one. So, this is plus beta plus 1 times RE equals. So, transpose natin sa right-hand side yung ibang terms. So, we have VEE minus VBE. Now, we can substitute the values for the given resistances, the given beta, the given voltages. Right, so we have IB equals VEE is equal to 20 volts. VBE is equal to 0.7. Bakit? Kasi naka-forward bias yung base and emitter junction natin. So positive to P-type and negative to N-type. Meron tayong 0.7 volt voltage drop between the base and emitter junction. Divided by, or all over, 240 kilo ohms, which is your R sub B, plus, ang given na beta is 90. So 90 plus 1, we have 91. And then we have RE of 2 kilo ohms. I sub B is equal to 45.73 microamperes. So that is the value for the base current. But how do we solve for I sub E? We can use this equation. We have I sub E equals beta plus 1. So we have 90 plus 1. We have 91 times 45.73 microamperes. So I sub E is now equal to 4.16 milliamperes. Those are the two currents na hahanapin natin muna for now. And then later on, we'll solve for the output voltage VCE. Now let us proceed to the collector and emitter terminals, or the collector emitter side, which is actually your output side para sa common collector configuration. I have drawn the collector emitter terminal side, which is the output side. No? Dinisconnect ko muna yung base because hindi naman siya kabilang sa ating collector and emitter terminals. Now let us write down the induced polarities and the voltages and the currents. This is minus, so this is minus plus. Minus plus because we're getting VCE. Alright? Next, we can now write down the KVL equation. We can do it clockwise again. But what is the current that passes through RE? IE ang dumadaan sa kanya. So we can draw it here. This is IE. So let's write down the KVL equation. Papasok tayo dito. So this is positive 20 volts. So idirekta na natin, no? Yung mga given natin. This is minus IE times RE. IE is solved as 4.16 milliamperes. Yan yung IE natin, or I sub E. Multiply natin sa R sub E, which is equal to 2 kilo ohms, minus VCE. Minus VCE is equal to 0 volt. Yung subscript na Q na hinahanap is represents your Q point, which is napag-aralan nyo naman sa Electronics 1, so I don't have to explain it anymore. Right? And then rearrange the equation in such a way. Now VCE is equal to 20 volts minus 4.16 milliamperes times 2 kilo ohms. The collector emitter voltage is equal to 11.68 volts. Right? So that is your VCE or VCEQ. We have a second example for the common collector configuration. For this circuit, meron tayong ibang variation for the common collector configuration. This time, yung RB natin is connected to a power supply, which is now called VCC. The collector is connected to your VCC also. And the emitter, kung mapapansin natin, yung RE, wala nang supply sa ilalim. Unlike yung naunang example natin, meron tayong negative supply. This is just another variation of the common collector configuration, although we can also use the variation or rather the circuit na diniscuss natin na nauna dito. Determine I sub B, I sub E, and VCE. So these are all DC parameters. Sa next discussion natin, we will discuss the AC parameters naman ng common collector configuration. For this one, in order for us to solve for I sub B, kukunin natin dito yung base and emitter sides, yung parang ginawa natin kanina. All capacitors are considered to be open circuit pagdating sa DC analysis. Let us just draw here first the base and emitter terminals. We're going to bend yung VCC pakaliwa. So we have 12 volts here for VCC. And the negative terminal of the VCC is connected to the ground. Konektado siya dito sa ating RP, which is equal to 220 kilo ohms, which is connected to the base. Collector, i-leave muna natin siyang nakahang or isolated. And then we have RE, which is equal to 3.3 kilo ohms. Ang susunod na step naman dito is to write down the induced polarities and the current. So, paulit-ulit lang yung gagawin natin for DC analysis. No? Similar methods to determine the DC parameters. Alright? This is plus, and then minus. We also have plus here, and minus. So, tignan natin, naka-forward bias ba yung base emitter junction? Positive to P-type, negative to N-type, yes. Therefore, magkakaroon tayong 0.7 volt voltage drop between the base and emitter junctions. So we will call that VBE. Right? Positive yung taas ng RE. And negative naman yung nasa baba niya. Next naman yung kuryente. Yung kuryenteng dumadaan kay R sub B, since konektado siya sa base, is called IB, of course. No? Papasok ang direksyon ng IB. How about IE? Pababa or palabas? Yeah. So now we have determined the induced polarities and induced currents. We will now write down the KVL equation of the base emitter terminal side. KVL. Let's do it clockwise. So this is minus 12 volts. So i-directa na natin, no? Lagay na natin yung may mga values. Minus 12 volts plus ID is unknown. That's why nilagay muna natin siya as a variable. Multiplied by RP, which is equal to 220 kilo. So i-directa na natin. Plus VBE. Since naka-forward bias yung ating base emitter junction, meron tayong 0.7 voltage drop between the base and emitter junction. Next, we have plus I sub E or IE is unknown. Sulat natin si IE. And then we have 3.3 kilo ohms equals 0 volt. So this is the KVL equation for the base and emitter terminal side. Combine natin yung dalawang term na may IB at IE. Again, alam natin na ang IE is equal to beta plus 1 times IB. So kung mapapansin natin, similar ito dun sa naunang variation ng common collector. Pagsamahin natin yung mga may IB na terms. IB times 220 kilo ohms. Instead of using IE, gagamitin natin itong equation na to. So we have beta plus 1. Beta is 100. So i-directa na natin. 100 plus 1 is 101. Right? Times 3.3 kilo ohms equals i-transpose natin sa right side yung 12 volts and yung 0.7. So 12 minus 0.7 volt. Calculating the value for I sub B, we have 20.42 microamperes. Next, we can now solve for IE. Kasi direct substitution lang naman. This is equal to 100 plus 1, we have 101. Multiplied by 20.42 microamperes. Therefore, IE is equal to 2.06. So, i-round off natin to 2 decimal places. 2.06 milliamperes. We have IB of 20.42 microamperes and IE of 2.06 milliamperes. Now let us proceed to the collector and emitter terminal side, which is actually the output side of the common collector configuration. I have drawn the collector and emitter terminal side. This is similar dun sa mga sinusolve natin before for the common emitter configuration, di ba? So we have yung VCC, binend natin pa kanan, directly connected siya dun sa ating collector. Now we can write down the induced polarities and currents. Again, susundan lang natin yung orientation ng ating VCC. We have positive, plus dito, and minus dito. This is your VCE, which is the output voltage for the common emitter and the common collector.
Pero yung output kasi natin, kinukuha talaga natin yung AC, yung nakuha natin dito sa emitter side. Alright? And then we have plus and minus. Anong kuryente yung dumadaloy dito sa ating RE or sa R sub E? I sub E. Therefore, pababa yung ating I sub E. Alright? Now we have the induced polarities and the induced currents. Let's write down the KVL equation. Let's do it clockwise. KVL. We have minus IE is calculated to be 2.06 milliamperes. Pwede na natin idirekta. This is 2.06 milliamperes times RE of 3.3 kilo ohms minus VCE plus 12 volts is equal to 0 volt. Alright. Now let us rewrite the equation. Ang hinahanap natin is VCE. So we have VCE equals 12 volts minus 2.06 milliamperes times 3.3 kilo ohms. 5.20 volts. That would be all for now. Our next discussion will be all about the AC analysis of the common collector configuration or the emitter follower configuration. Have a nice day.